Hello students, welcome to lecture 13 of our online chemistry classes. I have given some homework in the last class. I hope that you might have completed that homework. In last class we have learned about we have solved numericals regarding the pH, pOH, K, alpha, C, and if we have learned pH, how to calculate hydronium concentration. That practice also we have done in last class. Now we'll go ahead and we'll learn the next theory concept. It is the equilibrium constant. Equilibrium constant of polybasic acid. Polybasic acid and polyacidic base. Now, before looking into the exact equation, we should know what we mean by basicity of acid. So, basicity of acid is nothing but number of replaceable H plus ion in acid. For example, HCl gives H plus plus Cl minus. That's why we can say that basicity is 1 because there is only one H plus ion. If we consider H2C2O4, it gives 2H plus ion, oxalic acid, and form this oxalate anion, and we can call this as the basicity. It's 2 here. Now you can tell me the basicity of sulfuric acid, H2SO4. It forms 2H plus ion and sulfate anion. 2H plus ions are formed. That's why we can say that basicity is 2. If we consider H3PO4, it forms 3H plus ion and phosphate anion. As there are 3H plus ion which can be released or replaced from this acid, we can say basicity is 3. Poly means many. Many means more than 1, 2, 3, 4, 5. It's called as poly. So basicity is 2, basicity is 3. This type of acids we call it as polybasic acid. If we consider the H2X as a general example, and if we put into aqueous medium, it forms H plus ion in first step and HX negative, and let the equilibrium constant for this reaction is Ka1. 1 because first step, K because equilibrium constant, and A because this is a weak acid. In second step, this HX negative anion again gives this H plus. That's why we call it as diacid. And H2 negative. We call it as Ka2. If we add all these two equations together, HS negative, we can cancel because it is appearing at two different sides. And we can write H2S aqueous. It forms 2H plus aqueous and H2 negative. And we write this as Ka, equilibrium constant of this overall reaction. We can say Ka equals to Ka1 multiplied by Ka2. We can do this. Ka1 is nothing but H plus square H2 negative divided by H2X, whereas Ka1 is nothing but molar concentration of product, Hx negative H plus divided by H2X multiplied by Ka2 is nothing but H plus H2 negative and Hx negative. Then we can say that this Hx negative we can cancel, and this side also H plus is nothing but H plus square x minus 2 H2x, which is same here. So we can say K equals to K1 into K2, because we have just added, and when two reactions are added, the equilibrium constants are multiplied. This we have seen long back in the chemical equilibrium. Now, if we compare K1 and K2, we always found that K1 is greater than K2, and if it is tribasic acid, it is greater than K3 also. It means the dissociation constant decreases as more and more H plus ions are removed. Why it is so? Because it is easy to remove H plus ion from H2X, but it is difficult to remove H plus ion from Hx negative, because Hx negative is comparatively smaller size, and from that smaller size, if we want to remove H plus ion, then we need to spend more energy. That's why the reaction will not favorable in the product side, and thereby it has lower value of Ka. So we have two relations. This relation already we know. For polybasic acid, Ka1 is greater than Ka2 is greater than Ka3. For polyacidic base, what we mean by acidity of base? Acidity of base is nothing but reverse. Acidity of base is nothing but number of replaceable OH negative ions in base. If we have calcium hydroxide, what is the acidity? As there are two replaceable OH negative, it is diacidic. Aluminium hydroxide, the acidity of this base equals to 3. Which relation holds good for this? Kb equals to Kb1 into Kb2, just like K equals to K1 into K2, and Kb1 is greater than Kb2 is greater than Kb3. The relation is same here. It means the more and more OH negative ion, if it has to be released, then in first step that release is more, in second step it is decreased, in third step again it decreases. So this is the important point we are noting here for the polyacidic bases and polybasic acids. Their equilibrium constant go on decreasing. This is the point which we want to stress here. So this is one important concept in case of more than one replaceable H plus ions and OH minus ion. Now we'll go ahead and we'll learn about the factors affecting the acidic strength. Very important concept. You should know what are the factors which affect the acidic strength. There are two factors which affect the acidic strength. We should understand them and we should apply them. See what we mean by factors affecting acidic strength. Factors affecting acidic strength. The first factor is the strength of HA bond. What is this H? H plus ion, which can be donated. H is acid, and it can replace H plus ion, releases H plus ion. That's why we call it as it has acidic nature. Now strength of HA bond, we can write that as strength of HA bond decreases. If the strength of this hydrogen and A decreases, energy required to break HA bond also decreases. Low and low energy is required. Strength is weak here. And that's why we can say that strength of or acidic strength of HA increases. Means it is inversely proportional. If stronger is the HA bond, weaker is the acid. If weaker is the HA bond, stronger is the acid. Why we say so? Because if this bond is easily broken, then only H plus ion can be removed. And when H plus ion is removed, we call this release. We call it as substance is in acidic state. Now we will mention here one point, that as we move from top to bottom, of course in a group, in a periodic table, in group, acidic strength increases because HCl bond length is shorter. That's why it is difficult to break that bond. HCl bond is having greater bond length. You are learning chemical bond. The bond length is one of the bond parameters. So this is easy to break. HBr is still easy to break. And HI is more easy to break. This can be broken easily. That's why we can say the acidic strength of HCl is less than HCl, is less than HBr, is less than HI. Why it is so? Because in HCl the strength between hydrogen and fluorine is greater, bond is difficult to break, H plus ions release is difficult, weak acid. HI, the bond between here hydrogen and iodine is big, easy to break, H plus ion can release easily, that's why acidic strength is greater. So this is first factor, strength of HA bond. It will decide the strength of acid. Another is the polarity of HA bond. Now polarity is due to electronegativity difference, that also you are learning. So we can say that as electronegativity difference between H and A increases, bond polarity increases, cleavage means breaking of HA bond easily it is broken. Easily broken means H plus ion can release easily. And that's why we can say acidic strength of HA increases. So as bond polarity increases, acidic strength increases. They are directly proportional. We will take one example. As we move from left to right in periodic table period, electronegativity difference increases, bond polarity increases, and that's why acidic strength increases. For example, methane, NH3, H2O and HF. We know that electronegativity of carbon is less than nitrogen, less than oxygen, less than fluorine. Fluorine is most electronegative element of the periodic table. So electronegativity difference in CH is less than NH is less than OH is less than FH. More electron difference is here. So polarity, bond polarity, less in methane than ammonia, than H2O, than HF. And that's why, which is stronger acid then? No doubt, the bond polarity is greater in HF, so HF is stronger acid. Because bond polarity is greater, electron difference is larger, bond is easy to break, H plus ion can be released easily, acidic strength is greater. That's how we can correlate all these things. So these are the two factors which affect the acidic strength of an acid. Now, after completing this acidic strength, we will see this in questions, how to identify which is stronger acid and which is weaker acid. The next is the buffer solutions. Next concept is of buffer solutions. Buffer solutions. Now, what are the buffer solutions? Solutions is their definition, which resist means suppose, which resist change in its pH. Resist change in its pH means it won't change its pH on addition of small amount of acid or base into it. So there are certain solutions which won't change their pH value, and this is very critical in biological fluid. We have seen in question the pH of blood is 7.3, slightly basic. It should remain same, otherwise it will lose its utility as a biological fluid. Human saliva has particular pH. If that pH gets changed, the complete digestion process gets disturbed. So there are certain solutions which are present in a biological system which does not allow the pH to be changed. Such solution resist change in pH, and those solutions which resist the change in pH, even though some acid or of course small amount, if we add more amount then naturally the pH is bound to be changed, but if small amount of acid and base is added, then their pH won't change. Such as solutions, we call it as the buffer solution. Now there are two types here, types of buffer solutions. First is acidic buffer and another is basic buffer. There is no neutral buffer because neutral base pH is 7. There will not be change in that pH. So this buffer concept is applicable only when there is change in pH. That's why we won't have a neutral buffer. Now in acidic buffer, first point we can say that pH is less than 7 because that's what we mean by acidic buffer. Then what is their composition? How they are made up of? It is nothing but weak acid, and its salt with strong base. Example, acetic acid, you know that it is weak acid, and CH3COONA, sodium acetate. Its salt with strong base. Which is strong base is sodium hydroxide. Sodium hydroxide loses OH minus ion. Acetic acid loses H plus ion, and they form this salt in neutralization reaction. So this is the example of acidic buffer because it contains weak acid and its salt with the strong base. Now what is the pH of this acidic buffer? pH is equal to pKa plus log of molar concentration of salt divided by molar concentration of acid. The derivation is not there in our syllabus. In fact, equation is also not there in the syllabus, but as a just additional information, we are looking into it. So this is the formula to calculate the pH of acidic buffer. pK plus log of concentration of salt divided by concentration of acid, because it has salt and acid. That's why. If both are equal, log 1 by 1 is log 1, log 1 is 0, pH is equal to pK. In that way we can calculate. Of course, I have already told you that this calculation is not there in this particular reduced syllabus. Now regarding the basic buffer, we can say that pH is greater than 7. And what is their composition? Ingredient, how they are made up of? Weak base plus is its salt with strong acid. Example is ammonium hydroxide plus ammonium chloride. Ammonium hydroxide is a weak base. Ammonium chloride is a salt with strong acid, which is strong acid is HCl. HCl gives H plus ion, then H4OH gives OH minus ion, and they form an H4Cl salt in the neutralization reaction. How to calculate its pOH? pOH is equal to pKb plus log of molar concentration of salt to base. Molar concentration of base. This is the formula to calculate this. Now, how they able to resist the change in pH? I will explain here, particularly acidic buffer, how it occurs. So these three main important points you have to remember. Acidic buffer is less than, pH is less than 7. It is nothing but weak acid and its salt with strong base. Example is acetic acid and sodium acetate. pH is equal to pK plus log molar concentration of salt divided by molar concentration of acid. Basic buffer is pH is more than 7. It is made up of weak base and its salt with strong acid. NH4OH plus NH4Cl is its example. And pOH is equal to pKb plus log of molar concentration of salt divided by molar concentration of base. Now we'll see the mechanism of the acidic buffer. Mechanism of acidic buffer. How this acidic buffer works. Mechanism of acidic buffer. There are two components into it. One is this acetic acid, which is weak acid, and another is sodium acetate, which is strong electrolyte because salt, so it is strong electrolyte, and this gives CH3CO negative plus H plus ion. Now if we add H plus ion into it from added acid, if we add acid, H plus ion will be released by that acid. It combines with this acidic ion from buffer and it forms CH3COH, which is weak acid. Alpha is low here. That's why pH remains same, because it will not release much H plus ion concentration. The H plus ion concentration we added, but it has been consumed from the acidic ion and its pH remains same if acid is added. If base is added, it will release OH negative ion from externally. If we add base, it combines with H plus ion and forms H2O, which we know that very weak electrolyte, and that's why alpha is low. And again we can say the pH remains same. So even though we are adding small amount of acid, H plus ion being consumed, we are adding small amount of base, OH minus ion also being consumed, and result is very weak electrolytes are formed out of it, which literally do not produce any H plus ion. That's why pH will not get affected. That's how the acidic buffer works. How basic buffer works? We have to see its mechanism. Now, I think you can write mechanism by your own. You understood exactly how this works. So, mechanism of basic buffer. There are two components. One is ammonium hydroxide, which is weak base, and it starts with strong acid. And this gives NH4 plus and OH minus. If H plus from added acid here, it combines with OH negative ion, which is released from this buffer, and it forms H2O. We know that H2O is a weak electrolyte, and that's why alpha is low and pH almost remains same. If we add OH negative ion in the form of base, it combines with ammonium ion. This ammonium ion is also in from buffer, and it forms ammonium hydroxide. And this is, we know that it's a weak base, that's why alpha is low and pH remains same. So whether we are adding acid, there is one component of buffer which consumes that. Otherwise, if we add H plus ion concentration will be greater, pH will be reduced and solution becomes more acidic. But this doesn't happen because H plus ion is being consumed. If we add base, OH minus ion also being consumed, and they form such a product which ionizes to very less extent, and that's why the pH remains same. This is how the buffer works. So this is very important type of solutions, buffer solutions. Important for us is definition of buffer solution. An example of acidic buffer and basic buffer, because already I have told you that there is no equation which is to calculate pH and pOH of buffer is not there in our slides. Now the next concept after this is the common ion effect. Common ion effect. This is also very important concept, always asked in theory 1 or 2 marks. Common ion effect. Common ion effect. First we will see the definition. It is the separation. Separation is decrease. Depression. Depression word we use it for mind, isn't it? Just like in lockdown, we said our minds were depressed, right? So depression is for mind. So separation, we use it for other things, but main thing is it is decrease. Separation of degree of dissociation means alpha of weak electrolyte by addition of strong electrolyte having common ion into it. This is called as common ion effect. Separation of degree of dissociation of weak electrolyte. Already weak electrolyte has lower degree of dissociation and still we are decreasing it. How? By addition of strong electrolyte, but not any strong electrolyte. That also should produce ion, which is common between weak electrolyte and strong electrolyte. We'll take the example. CH3COOH aqueous, it forms CH3CO minus aqueous acetate ion and H plus ion aqueous. This is, we know that it is acetic acid and it is weak acid. Why it is weak acid? Because it releases less amount of H plus ion. How will come to know it has released less number of H plus ion? The Ka is low, that's why it is weak acid. Equilibrium constant of the dissociation reaction is lower. If we add into it sodium acetate, which is a salt, and being salt, it is strong electrolyte. It also dissociates and it forms acetate ion and Na plus ion. Now both of them are releasing acetate ion. So you can say common ion is here, acetate ion, isn't it? Because acetic acid also releases acetate ion and sodium acetate also releases acetate ion. So it is common ion. Now concentration of acetate ion increases because both of them are producing like that. But as concentration of product increases, equilibrium will shift in that direction to decrease that is towards the left side. And when equilibrium shift to left side, we get more and more acetic acid. So forward reaction is suppressed, backward reaction is favored. And forward reaction is dissociation. So dissociation is suppressed. That's why we said separation of degree of dissociation. So acetate ion concentration increases according to LECTURE-13 principle. reverse reaction is favored. That's why degree of dissociation of acetic acid decreases, and that decreases nothing but depression. Depression of degree of dissociation of weak acid by addition of strong electrolyte containing common ion into it is called as the common ion effect. This is one example. We can give another example also. NH4OH and NH4Cl is also example for this. NH4Cl, NH4OH gives NH4 plus OH negative. NH4Cl gives NH4 plus Cl negative. This is common ion. Molar concentration of ammonium ion increases. Degree of dissociation of ammonium hydroxide decreases. So this degree of dissociation has decreased for weak electrolyte by addition of strong electrolyte. That's what we call it as the common ion effect. So very simple definition: separation of degree of dissociation of weak electrolyte by addition of strong electrolyte containing common ion, having common ion into it, is called as the common ion effect. And two examples: CH3COH, CH3COA, their dissociation, and one sentence point right. So this is also question of 2 mark, common ion effect and its example. Now we'll go to the last theoretical concept called as solubility product. Solubility product of salt, of course. Dissociation constant of acid Ka, dissociation constant of base Kb. Now we are learning about the solubility product, which is nothing but K, Sp, S for solubility, which stands for product, of sparingly soluble salt. Now sparingly soluble means less soluble, and salt is nothing but acid plus base gives salt plus water. We know that the substance formed after neutralization of acid and base, we call it as a salt. It may be acidic, it may be basic, or it may be neutral, depending on from which acid and which base it has been formed. Now what we mean by sparingly soluble? Sparingly soluble means very less soluble. So all the salts, they do not have same solubility. Now why they don't have same solubility? Because solubility depends on two factors. Solubility of salt depends on two factors. One is called as lattice enthalpy. Enthalpy is nothing but energy. And another is called as solvation energy or solvation enthalpy. Enthalpy and energy will take it in same context. So when salt is put into water, the first thing happens is that oppositely charged ions get separated. We call it as the energy required to remove these electrostatic forces and release of ions as the lattice enthalpy. And once ions are formed, they get stable by solvation. For example, if we take NaCl, a solid state, and if we put that into water, it forms Na plus ion Cl minus ion. We'll take this beaker and put this NaCl into this water and form these two types of ions. Now this Na plus ions and Cl minus ions get separated by the energy called as lattice enthalpy. But after the separation, this Na plus ion is stabilized by the solvation. Solvation means what? All around this Na plus ion, H2O molecules comes to surround this, to make it stable, such that oxygen is nearer to Na plus. Why? Because in between hydrogen and oxygen, which is more electronegative oxygen, so it carries delta negative charge, it carries delta negative charge, all this. So this positive charge and this negative charge, this gets stabilized, and energy is released due to their stability, and that is called as the solvation energy. Same thing happens to Cl minus, but in reverse way. H2O molecules will come but from hydrogen side now. Why it is so? Because hydrogen has partial positive charge, like this, and this Cl negative has charge, so there is a opposite charges. That's why they get stable by its opposite charges. So this solvation energy is released and this hydration energy is absorbed. If solvation energy is greater than lattice energy, then salt is soluble. If lattice energy is greater, it means it requires more energy to separate than the energy released by solvation, then the salt will not get dissolved. So salt will get dissolved if ions formed from it are stabilized by the solvent and the energy released, solvation energy, is greater than the energy required to separate those ions, which we call it as the lattice energy. So depending on that, we have classified salts into soluble, slightly soluble, and sparingly soluble. Soluble means they dissolve completely. Slightly soluble means their solubility is lower. 0.1 molar solution they form, less than 0.1 molar. And sparingly soluble means 0.01 molar, less than 0.1 molar. So those salts which has very very low solubility, we call it as sparingly soluble salt. Those which are having greater solubility, we call it as soluble salts. And those which are having less solubility than soluble salt, but greater than sparingly soluble salt, we call them as the slightly soluble salt. So we have soluble salts, slightly soluble salts, and sparingly soluble salts. Why the salts are sparingly soluble? Because their solvation energy is relatively lower. And why the salts are more soluble? Because they have greater solvation energy. So there is difference in the magnitude of this solvation energy, which makes salts soluble, slightly soluble, and sparingly soluble. Now from our equilibrium point of view, we will discuss about the sparingly soluble salt, because they are not dissolved completely. So there is always a possibility that we have ions form and we have undissociated salt. And there is equilibrium, and that equilibrium we have to study, because we are learning equilibrium only. So this equilibrium also very interesting, and we should take account of that. See how this equilibrium is studied. We will take silver chloride, which is example of sparingly soluble salt. Put into water, aqua means water, and we get Ag plus ion and Cl minus ion. rate of forward and rate of reverse reaction becomes equal. Equilibrium is established. At equilibrium, what is present? Ions and undissociated silver product. We try to write its equilibrium constant K. Ag plus Cl minus and AgCl. But this AgCl is in solid state. So concentration of this AgCl is assumed to be 1 unity. So this K becomes KSP, solubility product. Ag plus Cl minus. So this is called as solubility product. How to define it? It is equal to product of molar concentration of cation and anion raised to powers, which are nothing but number of ions formed from 1 mole of such in saturated solution. Because only in saturated solution this equilibrium can be established. Saturated solution is the capacity, maximum capacity of that solvent is reached to dissolve that salt at given temperature. This is the definition of solubility product. Listen once again. Product of molar concentration of cation and anion raised to powers equal to number of ions formed from 1 mole of salt in a saturated solution at a given temperature is called as solubility product. Now we will consider this example. BaCl2, solid and aqueous, and they form Ba plus 2 aqueous and 2Cl minus aqueous. How to write its KSP? KSP is equal to Ba plus 2 raised to how many moles are formed? 1 means no need to write it. But Cl negative, 2 are there. So I write 2 there. So it is raised to power of number of ions formed from 1 mole of electrolyte. If we have say aluminium sulfate like this, sulfate balance is 2 and aluminium is 3. Solid plus aqua and 2Al3 and 3SO4 negative ion aqueous. What will be its KSP equation? KSP equals to Al plus 3 square and SO4 minus 2 cube. We can calculate KSP values if we know their concentration. Solubility product can be calculated. So important thing is definition of solubility product, and to understand that it is applicable to sparingly soluble salt, because in sparingly soluble salt we have dissociated ions and undissociated salt molecule in equilibrium, and how to write its expression. We will classify this sparingly soluble salt into different type and we will arrive at formula and use it in next class. So in this class we have learned about the polybasic acid, polyacidic bases, the factors affecting strength of acid, buffer solution, common ion effect, and definition of solubility product and example. So very important part. Revise it, understand it, practice it. Thank you for watching this video.